Let's have a closer look on fragmentation, because fragmentation in IPv6 differs from fragmentation concept in IPv4. Already mentioned, we have the basic headers, and we have possibly various extension header, and then we have the load. And now let's assume that this data package is too long to be transported to a network on the path from the sender to the receiver. Then, same idea, this package is fragmented into several packages, and these packages which have a size that's not exceeding the size of data packages that are allowed to be transported through the network. And then this package has to be subdivided into several pieces. But of course, each of the fragmentation packages containing some fragmentation information needs a new header, needs to contain all the information that's available in the extension header of the original data packet, and then newly the fragmentation header is needed to explain the way the data package was fragmented, to give the receiver a chance to reconstruct the original data package. So here you see in the user data, this is the first part of the information, the header, the original header with the extension header, and then the starting part from the load. In the second fragment here in the user data, there are only this part of the load and in the other parts of the load. But what's important, each fragment needs to be extended by the original header situation plus the fragmentation header. So this is the original situation, and this is newly coming the fragmentation header containing all the information that's needed to deal with the fragmentation. In this way, we can very clearly see that such a concept, of course, has the need that there are more administrational data needed than in the original part. In the original part, we have this as the administrational data compared to that of the load. In the fragmentation part, the ratio between administration data and load is much worse. But what should we do when the original data packet cannot be transported through a network? Now let's see another point. Fragmentation is differing in IPv6 to IPv4. In IPv6, the principle of end-to-end fragmentation is implemented. This means that the IPv6 routers are freed from the task of fragmentation. In the IPv4 network, each router was checking whether the data package may be transported to the next hop, or whether the network it has to be transported to reach the next hop has a smaller MTU. And if this was the case, the router started the fragmentation according exactly to that subsequent network. To free router from such work, in IPv6, the principle of end-to-end fragmentation is implemented. That means that routers expect fitting IPv6 datagrams. That means that the sender is responsible to fragment the packets in such a way that the fragmented packages have a size that fits to all the intermediate networks. So the idea is to free the routers of such work to make communication more efficient. But it brings the burden of the fragmentation away from the routers to the sender. Now the sender had to find out what is the right fragmentation size. What is the minimal MTU on the different networks the package has to be taken from the sender to the receiver. And that's difficult, because that means that the sender has to find out what information about the path from the sender to the receiver. What the sender needs to find out is the minimum MTU. This was a maximum transmission unit. And the idea here with IP version 6 is to define a minimum MTU, MTU by 128 byte, and that in an IPv6 network, it's assumed that any network connected to the internet has an MTU that's not smaller than this minimum MTU. And then the sender can start to fragment packet in such 128 byte packets, and then the sender can expect that all the data packets have the right size and to be transmitted through the different networks. But in many cases, this is inefficient in a way that too much fragmentation is needed. So there is another mechanism in IPv6 to find out what is the minimum MTU on the path from the sender to the receiver. And this mechanism is the so-called path MTU discovery. So to find out what is the minimum transmission unit on the path from the sender to the receiver. What are the problems with this minimum path MTU discovery? Of course, this restricts the flexibility, because if the MTU, the path MTU, is discovered for a certain path and the packet is taking another path, then it may be that on the another path there is a smaller MTU. And the principle that the packages can find their own path through the network, this was one of the basic things in this IP protocol and the IP routing. So if the package is rerouted, then rerouting of the package is no more possible without special efforts. Special effort means that for the new path, a new computation of the MTU, of the minimal path MTU, is necessary. Let's have a look to this mechanism of computing the path MTU. The IP version 6 routers do not fragment, so the sender is responsible. So the sender has to find out whether a packet size is too large for the transport to the receiver. What is the sender doing? He starts this path MTU discovery process. So the sender estimates the path MTU. So and the path MTU, that's the minimal MTU on the route to the receiver. So it starts initially with the MTU of the own local area networks, and then the router needs to find out whether packet size is too large for the route to the next hop and the next but one top. And not to check out it with a data package and then it's refused and then have to resend. The MTU discovery process is using ICMP messages, ICMP version 6 messages, packet too long, and this is received by the sender, and then he can adapt the length by fragmenting the data package. ICMP, we know this already from Internet Protocol version 4, also in case of Internet Protocol version 6, is a protocol for status and error messages connected to the IP protocol, and the packet too large message is not only to say no, it's too large, but it contains also the MTU of the next local area network, so that the sender knows, aha, this is the size the package has to be fragmented. So the sender can use this information, can perform a fragmentation, and then he can make a next try by sending the data package. And if it's fine, then the packages receive the destination. And if there is another local area network with a smaller MTU, then the sender gets an ICMP version 6 message, packet too large with the size of this network, and then he can perform a next fragmentation. If you remember last week, we had the problem that on different passes, packages which are already fragmented and are newly fragmented, that there are difficulties in reconstructing the original package. So you see this mechanism in IPv6 was exactly designed for the reason to avoid such problems. To say clearly, it's a problem of the sender. The routers, the intermediate systems are not deal with fragmentation questions, so they can react faster, and in this way the communication is organized more efficient. Here is some more new functionality of IPv6, and it's the so-called jumbo payload. And the idea behind is that IPv6 offers the possibility to transport datagrams with an oversized load of more than 65,000 bytes. You remember this was the maximal size, and the idea to allow such oversized datagrams comes from the experience that in this IPv6 network, video data are a big amount of the are an important type of data that need to be transported, and such video and audio data are very large. So the IPv6 designer came with a concept of jumbogram. Of course, it needs to be mentioned in the header that this is a datagram of this is a jumbogram. And this notification is done in the hop-by-hop options header. So here the router can recognize now a jumbogram is coming. So here we have the next header field, the header extension length type 195, option data type length 4, and then the jumbo payload program length. And this information is information that it's contained and summarized in the optional hop-by-hop header. So if a jumbogram is sent, then routers can recognize this in the hop-by-hop options header, and there are the lengths mentioned and the data type and other things.